Hello! A glider is a special type of aircraft, obviously because it does not have any propulsion system. It is designed to be able to glide at a very small descent angle. Therefore, it can travel great distances horizontally compared to the vertical distance. Perhaps you may wonder how it can get up to a high altitude in the first place. If this aircraft is gliding in a pocket of air which itself is rising, so if there is a vertical wind component, then the glider is still descending relative to the air, but relative to the ground it is in fact climbing. So when does this occur? In reality, the atmosphere is not at rest. Wind is present. There are local temperature differences and there are local differences in humidity. As a result of local conditions, such as a relatively warm area of the ground, a vertical motion of air may be created. A rising current of warm air is called a thermal, and in such a thermal, a glider can climb relative to the ground. Once a high altitude is reached, the aircraft can glide over a long distance to another thermal and restart this process. This is of course a very nice pastime. In terms of aircraft performance, the smallest glide angle that can be achieved is our main interest. There is also a different situation in which glide performance is important. Now this is the situation where a powered aircraft experiences a failure of all engines. Now failure of all engines may seem like a hypothetical situation for multi-engined aircraft. However, it may happen in case a plane runs out of fuel or, for example, when it flies through a cloud of volcanic ash, which has happened in the past. In this case, the main question is whether it is possible to reach the nearest airfield. Again, the glide angle is the determining factor in that respect. So let us figure out what the smallest possible glide angle is for a given aircraft and whether it is important to fly at a specific airspeed to achieve this. So, I start over here with the general equations of motion, and I've also written down the equations for lift and drag. Now, since we are in gliding flight, we can say that the thrust is equal to 0. Therefore, this thrust term becomes 0 and this thrust term as well. Now, since we are also interested in the smallest descent angle, gamma is fairly small. And for small angles, we can say that in fact the cosine of gamma is almost equal to 1. And it is a small angle, but it's also a constant angle, because the pilot makes sure to fly at that best glide angle all the time. So since it is constant, we can also say that the change of flight path angle with time is more or less equal to 0. Finally, we can also say that the change of airspeed with time will be fairly constant, because there is a specific airspeed, most likely, which is optimal. It may be changing very slowly as air density changes, but in a short amount of time, airspeed will not be changing very much. So therefore, we have that the change of flight path angle with time is also equal to 0. Now that gives us quite a simplified equation of motion. We have 0 is minus the drag minus the weight times the sine of the flight path angle. And the second equation of motion, which you see over here, basically states that lift is equal to weight now. So we're interested in the smallest descent angle, and the descent angle is in fact minus the climb angle. So I can write this equation as 0 is minus the drag plus lift times the sine of the glide angle. Now if I rearrange this, I find that the glide angle is the arc sine of lift divided by drag. And if I look over here, I can see that lift divided by drag is this equation on top divided by CD times a half rho v squared s, and then I can cancel out a lot of terms. So the glide angle is therefore the same as the arc sine of the lift coefficient divided by the drag coefficient. So it's only a function of aerodynamic parameters. The question is, at which airspeed should you fly to achieve a certain glide angle? And remember that lift must equal the weight. So therefore weight is CL times a half rho v squared s. And if we take the airspeed to one side of the equation, then we find that the airspeed is the weight divided by the surface area of the wing times 2 over the air density times 1 over the lift coefficient, and this of course is the same lift coefficient as the one in the glide angle equation. So in order to achieve the smallest descent angle, the aircraft must be flown at the lift coefficient which results in the best lift over drag ratio. If the lift drag polar is known, this is a constant value. Of course, the pilot cannot see what the lift coefficient is, but it is possible to calculate the corresponding airspeed. And this is something that the pilot can observe in the cockpit. Perhaps you have noticed something peculiar about this glide angle equation. It only depends on aerodynamic characteristics. Apparently, the aircraft weight does not play a role at all. So how does that work? The angle, highly exaggerated in this figure, is fixed by the aerodynamic characteristics. The airspeed, on the other hand, depends on the weight. So a heavy plane will reach the same distance as a light plane in case the aerodynamic characteristics are identical. The time it takes to get to the ground is, however, completely different. The heavy plane flies much faster than the light plane, and therefore it will reach the ground first. Now, the glide performance of sailplanes is quite different from the glide performance of commercial aircraft. Gliders can have glide ratios up to 1:60. This is the ratio of horizontal distance versus vertical distance covered. The glider design is dominated by aerodynamic performance, hence it has a very slender and straight wing, whereas commercial airplanes are more of a compromise between aerodynamics, propulsion and structures. Commercial airplanes should also perform well in other flight phases such as cruise, where besides the lift-over-drag ratio, also, for example, propulsive efficiency and airplane weight play a major role. As a result, a typical glide ratio of a commercial aircraft is in the order of 1:18. To conclude, we now have a simple equation to calculate the minimum descent angle in gliding flight, and we are able to calculate the corresponding airspeed.